Hello, James Spotton here from the Minnesota Space Grant. I'd like to talk to you a little bit about doing predictions, trajectory predictions for stratospheric balloon flights. Let me show you an example from a recent balloon flight just to show that this can in fact be done. So here I have a map. This map is a prediction. This is what was expected to happen for a flight. The flight took off from Glencoe, Minnesota. That's in the upper left-hand edge of this black trace. It ascends, going mostly to the south and slightly east, and then it turns and goes west. The star, pretty close to the town of Janesville, above the town of Janesville, indicates the burst altitude or the altitude at which this thing will stop going up. And then it does the same pattern, sort of backwards in reverse, faster. And so it continues to the west, turns to the southeast, and eventually lands perhaps slightly south and east of the town of New Richland. That was the prediction. Here's what actually happened. So we launched from Glencoe. It went down, it turned to the west, slightly north of Janesville. So in other words, the prediction had it going a little bit farther southeast, but it did go west. And then at that point, it started coming down and it turned back to the southeast. And considering that it didn't quite get as far south as was predicted, it landed a little bit north of New Richland instead of south of New Richland. Other than that, though, it actually worked pretty well. So the reason we use predictions is to make decisions about where to launch from, in particular so that we can land somewhere that has good recovery areas. It's possible to launch from most anywhere, but if you land in a lake, or if you land in a forest, or if you land in a place that has no roads, perhaps because it's a swamp or something, that's not great. So for my team, at least, we drive around and launch from a location that we like, which leads us to land in a location that we like. To understand how these predictions work, it's important to understand what features of a flight are sort of reproducible. So for this flight, here is the real track. The reason they're individual dots is because those are individual transmission points during the flight. But if I scroll down, here is an altitude vertically versus time horizontally graph. And I want to point out that this particular flight went up at almost a constant rate all the way to the peak. And the peak in meters was close to 30,000 meters, just shy of 30 kilometers. And then when it started to come down, notice it comes down very fast and then eventually slows and it lands at a very constant rate, perhaps slightly faster than the ascent. So you get to choose. You get to choose how fast things go up, basically by how much lifting gas you put in, compared to the size of the balloon, compared to the size of the payload. The bursting altitude will be related to the size of the balloon in particular and how much gas you put in to start out with, and hence how much stretch it has left. And so in this case, it got to almost 30 kilometers. And then the descent, which is nonlinear but very predictable, is related to the weight of the payload stack compared to the size of the parachute. And you get to choose both of those, okay? So to do the predictions, what you're going to do is you're going to indicate when and where you plan to launch from, the ascent rate, which on this graph you can see is very constant for a real flight. Sometimes it goes up at a constant rate and then it slows slightly and goes up at a new constant rate above maybe 15 kilometers. In Florida, supposedly it sometimes picks up speed. Here in Minnesota, it always slows down, but this flight where it didn't slow down at all, it just went at a constant rate the whole time. That's pretty typical for our flights. Okay, so you need to input the rate at which you will go up, and you can choose that based on how much you fill your balloon. You need to indicate the burst altitude. And so my predictions were done with a 30-kilometer burst altitude, and notice that that was almost exactly right for the flight. And then you need to indicate something about the descent. The descent is nonlinear, and so the prediction software I'm going to use just asks for how fast are you going when you hit the ground. So essentially, as this thing curves, it slows down slightly on descent, and it hits the ground at a specific rate, and that rate is not too different, in fact, from the ascent rate, and that will be another parameter. So let me go to a browser and show you what I would do for generating a prediction. You can't generate predictions for days that are in the past, so I'm going to pretend. I'm going to pretend that I'm going to fly in a few days' time. So the first thing I'm going to do, let's say that today's Sunday. Let's say I want to fly late this coming week, Thursday, maybe Friday. Let's take a look at, first of all, let's look at the weather and make sure the weather is reasonable. So here's what I choose to do. I go to Weather Underground. And I'm going to choose Owatonna. Owatonna, Minnesota is just a town south of the Twin Cities where I live, and we often fly in the vicinity of Owatonna. Once I choose an actual launch location, I will rerun this particular query for the actual town I choose. But for now, let me just try Owatonna. And it says, okay, what do you want to know about Owatonna? And I will click Show Me 10 days into the future. Frankly, a day or two or three, probably pretty reliable. 5 or 6 days, maybe fairly good. By the time it gets 10 days into the future, I wouldn't pay too much attention. So I'm going to definitely do this over and over again between now and the day of flight. But for the moment, I'm going to choose the 10-day look, and it will show me a graph. And here's what the graph shows me. First of all, it shows me that Monday is wet, and Tuesday is windy, and Wednesday is wet, and Thursday and Friday both are sunny. This is good. So in other words, it looks like Thursday and Friday are both possible days, but there is in fact a big difference. If I scroll down a little bit farther, I notice that Thursday, the bottom graph here, Thursday is very windy. It winds almost 20 miles an hour. And Friday is very calm with winds less than 10 miles an hour. This makes a really big difference when you're trying to launch a balloon, because controlling the balloon on the ground once inflated is very difficult if it's windy, especially when we're out and about and we're inflating outdoors. Some people are able to inflate indoors. That's great. That's not my life. But if you inflate indoors, presumably you have to choose where you're going to inflate from, like from your campus, and then you have to take what you get as far as launch, as far as trajectories. I prefer to choose where I launch from, and then I can indicate where I would like to land. Okay, so I'm definitely going to choose Friday over Thursday because of wind, not because Thursday is bad weather, but it's windy. That's fine. So the next thing I'm going to do is I'm going to go to balloon track online. So if I type the words balloon track online, I get a variety of tracking software. And I prefer to use the first one that comes up, CUSF Landing Predictor 2.5. This particular one isn't a product of England. I can tell that because the very first map they show me is England, and there's London there. So what I'm going to do first is I'm going to grab the area where I'm going to put my parameters in, which is often the right-hand side at the lower right. And you probably can't see my cursor, which is unfortunate, but I'm going to grab the little double arrows in the upper left part of that sub window and drag it over to the left-hand side. I just prefer to have it on the left-hand side, not the right-hand side. The next thing I'm going to do is I'm going to type in a latitude and longitude, which will get me to Minnesota. Not to where I'm really going to launch from, but at least get the map to show my environment. So we're very close to 45 degrees latitude and minus 93 degrees longitude. The minus there just means west of rather than east of Greenwich. So the location now is somewhere in the Twin Cities metropolitan area. It's in North St. Paul. I would not launch from North St. Paul. I would not launch from a city, but at least gets me the right map, a Minnesota map. So the next thing I'm going to do is I'm just going to test the waters here a little tiny bit. I'm just going to see for the day that I have in mind, which is Friday. And if today is the 12th, Friday would be 13, 14, 15, the 17th of June, and launching about noon local time. Okay. So Minnesota is fairly flat with an altitude of about 300 meters above sea level for the whole state. Okay. The launch time would be noon local time, which happens to be 1700 universal time. At this time of year, in the summertime, we're 5 hours different. Okay, so 1700 minus 5 hours would be 1200, noon. I'm interested in the 17th of June. Today is the 12th of June. The ascent rate of 5 meters per second. I'm going to leave that alone. That is almost exactly 1,000 feet per minute. And that's what we consider our classic or default ascent rate. And burst altitude of 30,000 meters, 30 kilometers, that's also pretty classic. So I'm going to leave that alone. The descent rate, on the other hand, I'm going to increase to 7 meters per second. So things land the way I set things up with our stack weights and our parachute selection. Typically, they land traveling a little faster than they go up. Okay, so here I have it. This is my original set. I just haven't chosen a good launch location, but I'm going to say run prediction and just see approximately how this thing moves. And what I notice is, as of now, it's not too different from that flight I just showed you. It goes mostly to the southeast. It cuts toward the west at altitude, and then it bursts and lands back to the southeast. Now I just want to move this thing around so that it lands in a location, a part of the state that I'm more comfortable with, and frankly launches from a part that I'm more comfortable with. So if I click on satellite view, I can see that to the east of us in Wisconsin, there's a lot of tree cover. And there's actually a lot of lakes in Minnesota. If I go back, those are more easily seen when I'm on the map. And notice lots of places that are pretty wet. So what I'm going to choose to do is I'm going to choose to fly somewhere so that I at least land south of Highway 14 that goes through Mankato, goes through Owatonna. Pretty much it's wet, pretty wet, lots of lakes north of that highway, and not too bad, a few lakes, but not too bad south of that highway. So I'm going to take a crack at launching from St. Peter. So St. Peter is north of Mankato. And if I click on set with map, and then it says, okay, now click on the map of the location. And it turns out that the window that I just opened up covered up the town of St. Peter. So I'm just going to move the map, and then I'm going to click. There it is, St. Peter, right above the middle of that extra window, St. Peter. And now I say run prediction. And now what I notice is that it pretty much does exactly the same shape, but it just is shifted over to a different part of the state. And before I get too wedded to St. Peter, I'm going to look at the landing zone. And so I'm going to zoom in on the descent and landing and just try to see how wet it is and how tree covered it is. So first of all, I notice there are some lakes around, but it's not too bad for Minnesota at least. And if I switch to satellite view, this looks pretty wide open. There are always a few trees in every square mile, pretty much in every farm location. But this is about as open in the state as it's going to get. So I would say this is a reasonable landing location. For now, I will rerun this before I do the flight because it's still several days away. But I'm going to go back up to St. Peter and now start thinking about where to launch from in the town. I just clicked on St. Peter as a town. Now I'm going to zoom in and take a look at some part of the town. So the first thing I notice is that supposedly this thing will travel south at first, and then it will hook a little bit west, and then it will start going to the southeast. So if it was a windy day, and even if it's not that windy, it's not a bad idea to look for some place that you can hide out of the wind, either because of tree cover or at this time of the year that works. In the wintertime, when there aren't leaves in the trees, hiding behind buildings is better, but buildings don't really block the wind, they just redirect it. So that's a little risky. But I am familiar with St. Peter, and in particular, I'm familiar with Gustavus Adolphus College because I've launched from their campus a few times. And I'm going to propose that we go to the Arboretum, which is on the west edge of their campus. Here is the parking lot for the Arboretum. I'm wheeling in. And my room has started to buzz. Hopefully that's not too much of a distraction. There's a parking lot which has trees around it. And so if the thing is going to be in a north to south wind, I could probably hide out of the wind by getting into this corner, the lower left-hand corner, in other words, the western corner of the parking lot. So let me say set with map, and I'm going to click right here. So that's right in the western edge of this parking lot. And now I say run prediction. And there it is. So it takes off from St. Peter. It travels between Mankato and Janesville. It turns around at altitude and overflies Waldorf. It bursts at 30 kilometers, and then it does everything in reverse faster and lands perhaps north of the town of Wells, somewhat in between, hopefully not hitting either Minnesota Lake or the lake near the town of Freeborn. Again, I would do this perhaps daily from now until Friday, possibly even doing one last look at this thing Friday morning before leaving campus and traveling, and adjusting things as necessary. In particular, adjusting my launch location to try and keep my landing location reasonable. For the record, other places in the state that I like to land, if not south of Mankato, Waseca, like this one, would be perhaps south of Owatonna, Rochester. In other words, maybe near Hayfield. problem is if I want to land this flight near Hayfield, okay, I would need to launch it from just south of the Twin Cities, perhaps Northfield or even points farther north. And not so anxious to do that. In general, I'm trying to stay away from the city, 40 miles away from the big airport, not because I have to, but because it's just good practice. Our stacks are always exempt, as in they're lighter than 12 pounds, so I don't have to stay away from big airports, but it's a good idea. Similarly, I will stay away from launching from towns that have airports themselves, even small airports. So the last thing I'm going to do is I'm going to go and get a look at the weather predictions for St. Peter itself. So, Weather Underground, St. Peter, Minnesota. I expect these will be very similar, but if this is where I'm going to launch from, I might as well look at the real deal. 10-day look. And interestingly enough, this concedes that it's going to be windy on Thursday. So basically it says Friday, sunny, Thursday, sunny, wind. The other one didn't say windy on Thursday, but I noticed that in that bottom graph. If I look at the bottom graph, I see that the winds in the middle of the day on Thursday are much stronger than the winds in the middle of the day on Friday. So my proposal would be go ahead and fly on Friday from St. Peter, but watch this prediction over the course of the next few days. Make sure it stays reasonable. Okay, that was a little bit about doing flight predictions. It turns out that there are actually a bunch of other predictors, online predictors, and there are even some downloadable predictors. In each case, of course, the predictor needs access to weather service data. Some predictors actually ask you to tell them which of the weather service locations, of which there are a finite number in any given state. In Minnesota, there's plenty or so. Tell them which one to look up. The predictor I'm using doesn't ask me to look up the weather service data. And the reason it doesn't is because it just looks for the closest one. It automatically does so. That's good. On the other hand, there are some predictors that will concede that you won't necessarily always have the same burst altitude, or you won't get your ascent rate just right, or maybe even your descent rate just right. And so they might do some random numbers, as in try a few ascent rates, try a few burst altitude, try a few descent rates, and here are a whole bunch of trajectories. What that allows you to do is look at a map and sort of see an area, not just a single landing spot, but an area. And depending on how scattered are the various trajectories, you might say, you know, we're pretty close to a forest and about half of those land in the forest. I probably want to move things around a bit and stay well clear of that spot. Similarly, if you notice that you are over, if you're not happy, if you really need a launch location, this might happen if you're, for instance, working with a school and you want to launch from a school location. That's unlikely for me, but it does happen for some people. It's like, yeah, I really want to launch from their schoolyard if I possibly can, but doing so will push me slightly too far. Well, then you have options. One option, for instance, is to overfill the balloon, making it go up faster, in which case it reaches burst altitude more quickly. It may well even burst a little bit lower because you expended some of the stretch in the balloon before you left the ground. But you can keep everything a little bit tighter and shorter because you fly up faster, you come down at the same rate, you don't fly as high. And so we talk about flying hot. That just means, in my mind, flying intentionally faster than 5 meters per second up. 5 meters per second, in some sense, is like a terminal velocity. And so you actually have to crank up the helium or hydrogen quite a bit if you're going to increase that speed. But you can have some sort of a standard as far as, you know, here's my stack weight, and if I multiply that by 1.25, perhaps for a K-mount balloon, 1.5 approximately for a Hoyi balloon, then you can go up at about 5 meters per second. And if I had a Hoyi balloon and I wanted to go up at 6 meters per second, doesn't sound like a lot, but it's about 20% extra, then I would probably need to increase from 1.5 to maybe 1.8 or something like that, as far as the amount of neck lift I want compared to the weight of the payload stack. So on the other hand, if you're really anxious to, well, you can also use a smaller parachute to come down fast. That would shorten up that part. So one recommendation I have, actually, especially when you're new to this, is to play around with the parameters. In other words, get your thing set for standard parameters and then say, well, what if I went a bit higher? What if I didn't get quite that high? What if I went up a bit faster? What if I didn't go up quite so fast? What if I, et cetera, And you'll find, this actually is surprising, you'll find that the landing location is very sensitive to certain changes you make and very insensitive to certain changes you make. For instance, in this particular flight, if I change the burst altitude, let me try it. I'll change the burst altitude from 30 kilometers to like 27 or like 10% less, or to 33, like 10% more, and just see what happens to the landing location. Let me go back to my share screen. Okay, so just take a look at this. Notice that it's landing not too far from Wells, slightly north, a little tiny bit east of Wells. Now, I'm going to increase the burst altitude by 10%, so I'm up to 33 kilometers. What that means is probably it's going to drift a little bit farther west at altitude, and hence it might land instead of north and slightly east of Wells. Well, we'll find out. There it is. Oops, a bit too much. So there it is. It landed north and a bit farther west of Wells. Okay, so in other words, that 10% change, kind of in the broad scheme of things, didn't change the landing location very much. But if you're looking at details, in particular, if you're watching that lake, that Minnesota lake, I'm much closer to that lake now. Or if I were to change this down to 27, so here's 10% less altitude, then notice that perhaps as expected, it doesn't drift as far west, and hence it lands farther to the east. Now it's pretty close to the lake near Freeborn. So interestingly enough, that 30 kilometers was a really good number. And I might want to think carefully about whether or not my balloon and stack weight do or don't support actually going to 33 kilometers. Try one more thing while I'm at it. Let me just say that, let's say I ascend at 4 meters per second instead of 5 meters per second. I somehow don't get enough helium, in my case, into my balloon, and it goes up kind of slow. Everything will be sluggish. I think what's going to happen before I even hit run prediction is it'll drift farther to the southeast because it's in those air currents for a longer period of time. It'll drift west at altitude, but probably will have gotten farther south before it does so. So here we go, run prediction. And there it is. Just as I was explaining, it drifts now somewhat farther south before hooking to the west. And then when it comes down, it lands southeast of Wells instead of northeast of Wells. On the other hand, if I were to fly hot, so let me say 6. Now I think that it will drift less during the flight and land even farther north of Wells than before. So I'm kind of mapping on a landing ellipse in some sense. So east and west is mostly, in this particular case, based on whether the first altitude was appropriately predicted. North and south is based on whether, in this case, mostly whether or not the ascent rate was correctly predicted. But I was happy with the original, but this allows me to say, and oh, by the way, on the day of the flight, if I happen to get 5.5 meters per second, I better drive a little bit farther south than I was expecting. Or if I happen to burst earlier than 30 kilometers, I probably better drive a little bit farther east. So a little bit about doing predictions. And in this particular case, I'm using a specific, rather simplistic predictor. If you have something complicated, like you're venting during a flight, or you're using 2 balloons and you let one go, which changes your ascent rate rather dramatically mid-flight, this predictor can't deal with that. So you either have to pretend, as in run multiple predictions. It's like, this is a prediction that gets me to altitude, and then now I'm going to float at altitude. So I'll use a completely different, I'll start at altitude and give myself a 0 ascent rate and just leave it up there for an hour or 2 or whatever the float time. You can cobble together a prediction in that way. On the other hand, there are other predictors, or you could write your own, that would allow you to have more parameters and input different parameters, allowing you to figure out more exactly where you will go. Good luck with your flying.